Hello, my name is Max Maximov, and today I'd like to present you my paper in Landmure made with co-authorship with Andrei Kalukin and Gennady Gorin, estimation of the pore size distribution of silica colloidal crystals. Let me introduce these nice materials called silica colloidal crystals, commonly known as opals. They find many applications in humidity sensing, photonic structures, and separation process. As you can see, this crystal is packed into an FCC lattice, and in another figure on the left you can see an SEM snapshot of mesoporous opals with their characteristic size of voids of about 60 nanometers. I'll clearly define the pore size later. First off, let's come up with the design for our model. Our first assumption would be that these pores, which are voids, can be represented as spheres. In the middle, you can see a slice of the solid filled with adsorbent, and it's shown that as it starts filling up, it starts to resemble a sphere. We hope that in the future we can verify our assumption by running grand canonical Monte Carlo simulations for small pores but with similar geometry, and to see the real picture in molecular snapshots. There are a few ways to characterize these materials using adsorption. One of the most common methods here is the use of the density functional theory, but unfortunately in the commercial software there are kernels with limited pore sizes available, typically up to 50 nanometers. In addition to that, their parameterization requires a lot of effort. This way we decided to go with a simpler model and see if it can describe the experiment with enough precision. The next method is the PGH theory, but unfortunately it only works for cylindrical pores. Despite the fact that there is an implementation for spheres, the application of this method is not common. As a result, we decided to use a simple model by Giriagin, which is plain, simple, has only two parameters to fit, and computationally cheap, so you can almost instantly get the result on your laptop. Let me first explain the theory. It consists of two parts. The main equation here is the Dirac-Barkov-de theory, which explains the relations between chemical potential mu, dejoining pressure pi, and the thickness of the film h. We also need a model for the dejoining pressure, which is unknown and can be modeled using, for instance, Frenkel-Halsey-Hill theory. Let me first explain how to find the parameters for the dejoining pressure. We first run an adsorption experiment for a material with macropores, not mesopores we finally want to characterize. So we can assume that our radius is infinite, and we can use the plain and simple linear regression to find the coefficients k and m. Once we found the exact parameters for the equation with the dejoining pressure using Frenkel-Halsey-Hill theory, we need to find how to build the final Dirac isotherms for various pore sizes. If you just apply the equation and try to plot the relative pressure versus density, you would see this figure. The catch here is that the equation only works until the point of capillary condensation and evaporation for adsorption and desorption branches respectively. To find these decision boundaries for the capillary condensation, we find the thickness where our derivative of chemical potential with respect to the film thickness is 0, and we use this thickness to calculate the corresponding value of the relative pressure. For the desorption branch, we proceed with a similar logic, but we set the condition of zero change of the Gibbs free energy on the complete filling. This way, you would transit from the raw model isotherms to the final ones, and you are now ready to build your own kernel isotherms. Then we proceed with the fitting of our experimental isotherm with experimental relative number density n subscript exp to fit with our kernel number density n subscript kernel to find the desired pore size distribution f. To solve it numerically, we transform the equation into the discrete form and solve it using linear regression with the non-negative constraint on the solution and put the penalty on the size of the solution by Tikhonov, also known as ratio regularization. To do so, we transform the equation into the equivalent form and then minimize the cross-validation score using generalized cross-validation criterion, which is an approximation of the leave one out cross-validation. Once we minimize it, we reconstruct both the solution and the isotherm. Let's consider our solution and look at it more closely. Somebody might ask why can't we just simply build the kernel and find a single isotherm which this kernel by minimizing the residual sum of squares. And it was indeed done in the previous paper. And in the next slide I'll show you the additional features which the weighted distribution can reveal. If you look more closely, the pore size distribution is bimodal. Our explanation is that this peak corresponds to two different types of pores which can be found in the opals. Here's the FCC packing of the crystal, and if you examine it carefully, it will have two types of voids, tetrahedral and octahedral. If you consider an ideal crystal, then the geometrical estimates would give the fractions of 0.631 and 0.368 of the sphere diameters. If you multiply these coefficients to the diameters of the sphere in the synthesized materials, you would see that these peaks would match pretty closely with the peaks in the found pore size distribution. It shows the advantages of this model over the single model approach. In addition to that, to cross-validate our result, we decided to carry out one more test and to modify the surface of our samples in such a way it would modify the strength of the adsorbed and adsorbate interaction, but won't affect the pore size. As you can see here, for the modified samples, the adsorption is weaker. Then we measured the isotherms one more time and got the new pore size distribution. It's clearly shown that our distributions match pretty well, which demonstrates the consistency of our model for both modified and non-modified samples. The next aspect we have to discuss is what branch we should choose, adsorption or desorption. And as we can see here, the desorption gives us pretty much inconsistent results. Although they are not so far off, they don't match closely enough to rely on. And our suggestion is that in the desorption branch we have pore blocking effects, so we can't really use this data for the construction of the pore size distribution. As a result, we decided to stick to the adsorption branch for this purpose. And here we go to the conclusion. First, we used Dirac theory and solved the adsorption integral equation to get the kernels and made them publicly available. Second, we are the first who extracted the pore size distribution from this type of material. Third, our approach allowed us to get the information about octahedral and tetrahedral voids in comparison to single mode solution. Finally, I like to say that our kernels and code are available on GitHub, and you can clone the repository, download the kernels, and look at the very nice tutorials written in Jupyter Notebook and how the theory works, how to use the rich regression, try to input your own data, and see the detailed explanation of the approach step by step. Also, all derivation is available in the original paper published last year in Landmirror. Plus, I'd like to express gratitude to my collaborators. So that's it, and thank you for paying attention.